artificial intelligence in one of the most hottest and most demanding domain. But wait, what is artificial intelligence? Artificial intelligence is basically an umbrella under which we have lots of domains, and one of the most used domain is deep learning. And how can we implement deep learning? In that, we are going to use some of the APIs, and Keras is one of them. And keep that in our mind that deep learning is one of the most hottest domain. So in that, we came up with a tutorial where we will learn about the API we use, that is known as Keras, to implement deep learning. So let's get started with the course.
All of you, please go into Jupyter, your Jupyter server. Do this import TensorFlow as TF. Or in fact, I've given this code to you. Just look for this code, TensorFlow introduction.ipynb. Open this code, don't execute it. TensorFlow underscore introduction.ipynb. Okay. In this, don't do anything, don't execute any cell. Just come straight down and do import TensorFlow as TF. Just execute this one. Import TensorFlow as TF. And please tell me whether it's running, it executes or not. Module not found error. Okay, then in that case, please install this line, pip install TensorFlow. Just say pip install TensorFlow 2.0. Yes, if you have an older version, you need to upgrade it, -u. Then those of you are getting this problem of TensorFlow, you have to install TensorFlow. So just say pip install TensorFlow 2.0. Those of you who have older version of TensorFlow, you do pip install -u, that is upgrade TensorFlow equal to 2.0. Let's go back to the presentation and look at what TensorFlow is. So in TensorFlow, I already discussed with you the name tensor. It comes from the fact that the data flows here in the deep neural network in form of multi-dimensional objects, which are called tensors in mathematics, right? This TensorFlow was a computing engine which was designed by Google for internal use, but subsequently they released it around 2 years ago as open source. And recently, around 6 months ago, they released the version 2.0. Between TensorFlow 1.0 and 2.0, there was a significant change. And hence, those who are working in TensorFlow 1.0, they have been advised to move on to 2.0 by Google itself. Very soon, TensorFlow 1.0 will be not supported. So we move to TensorFlow 2.0. So whatever discussion I'm going to have will be in the context of 2.0, the latest version. So we'll discuss what is TensorFlow, why is TensorFlow very popular in the market outside. I told you this morning, the competitor for TensorFlow is PyTorch. PyTorch is also open source, but that is from Facebook, this is from Google. We'll also discuss some of the changes that have happened in 2.x, but this kind of is not relevant here because you people have not used 1.x. But still, I will tell you what the changes are. Then we'll switch on to Keras. Keras is another tool which is made use of over and above TensorFlow to build all deep neural network based models. Okay, so you can build the deep neural network based models either using TensorFlow or using Keras. This is like you can write your SQL directly into Oracle SQL Server, or you can probably use Oracle Designer or any other tool to generate the SQL for you, right? So just like we can use a tool there to generate the SQL for us, here also we can use an API, a tool called Keras, to generate the TensorFlow script for us. So we'll see Keras and we'll be working in Keras. All the model building will happen in Keras. Though we are doing this on local laptop right now, my advice to you is to switch over to, if you're not already done that, to switch over to Google Colab. When you get into, you know what is Google Colab? Collaboratory, yeah? Anybody who doesn't know, you don't know? I'll just quickly tell you what Google Colab is. Google Collaboratory is an open source platform available to us from Google, where they give you the required computing power free, on which we build our models, import our data, build our models, test our models, and so on and so forth. What is the advantage of Google Colab is you don't need to worry about upgrades, version controls, and all these things. It's taken care of. Secondly, the kind of compute environment that is required for your capstone projects, our laptops will usually not suffice. So we will need both very heavy CPU power as well as memory, which is provided by this Google Collaboratory. So it's called Google Colab. For that, you have to have an account in Google. Once you have that, just go to your Gmail. First, make sure you have a Google Drive with you. Are you all with me? Yeah. On this Google Drive, first create a folder for yourselves. I've created a folder called Colab Notebooks. Jupyter Notebooks, I store them here. You upload all the notebooks that you have. Okay, you can use any notebook, decision tree, based logic, anything you can bring in here. And right click, open with Collaboratory. This will take you to a Jupyter Notebook environment, but on Google Cloud, where the resources will be allocated to you, both the hard disk and the computing resources. Right now, as of now today, this Google Colab still runs on TensorFlow 1.x. It's not 2.0. So if you want, you can upgrade it here. Pip install -u tensor 2.2. They'll allow you to upgrade also. What I'm saying is, you need to get used to this environment, because when you do your capstone, your laptops will not suffice. The volume of the data, the amount of calculations that need to be done, stored, and so on and so forth. But today's class, we don't need to go into Google Colab. We go straight into our local systems. So what we are doing right now is on our local laptops. Now here you please tell me now, are you able to import TensorFlow STF? Kindly confirm whether the version of TensorFlow is 2.0 or not. TF dot double underscore version double underscore. So this should give me 2.00. So let's start with what TensorFlow is, then we'll move on to Keras. So let me go back to TensorFlow. Now TensorFlow is a computing engine using which you can build any kind of model. It's more popular for deep neural network based modeling, TensorFlow. Fortunately, it's open sourced, and it's an end-to-end platform, which means here you can use functions available to get your data from various sources. You have functionalities available to clean your data. You have functionalities available to transform your data. You have functionalities available to build your models, test your models, and even deploy your models. So it's end to end, all the required solutions are available in this engine. That is one of the reasons why it is so popular. It's one of the most used deep learning libraries as of today, other than PyTorch. And it is very easy to learn, and especially when you're doing some kind of testing, research of deep neural network based models, this is the model to go to, especially version 2.0, which has shifted from the earlier version to a TensorFlow 1.0, used to follow a method called lazy execution, which means if you give your code, if you write your code in it, in the TensorFlow 1.0, all the code will be converted into what I call a to-do list. Basically, I have to do this, I have to do this, I have to do this, but none of the code will be executed until you come to a point and ask it to execute. Till that point where you ask it to execute, by giving certain commands, it has to execute the code. Till that point where you come and ask it to execute, till that point, it just keeps creating a to-do list. To be technically accurate, it creates a graph. The graph of the sequence in which steps have to be executed and on which data what needs to be executed. And subsequently, the graph will be transformed into an executable and executed. There are some advantages there, disadvantages there. The advantage there is, anybody from SQL background here? Any DBA kind of person? No? Database administrator? Are you okay with SQL, anybody SQL writing and all these things in databases? When you write any SQL in our database, say Oracle database, when I write any select query in the Oracle database on a table, what Oracle does is it converts that SQL query internally into a graph. It's called a query plan. It optimizes the graph. It says, okay, this is what the output is required and this is what the table is. What is the best way of doing this? The most efficient way. That concept is called query planning. Once a query plan is formed, the server actually executes the query for you and gets you the result. Same concept in TensorFlow 1.0. When you have a graph, at the point where you have to turn that graph into executable, it actually optimizes the graph. Are there any steps which are repeats? So let me execute once and store the result and use it again. Are there steps which can be executed in parallel? Are there steps which need to be executed in sequence? It will do all this analysis and accordingly create an exe for you, where the exe will be automatically distributed wherever it can be distributed. It will be reused wherever it can be reused, and so on and so forth, and your execution will be optimized. As a result, your operations in TensorFlow 1 compared to the same operations in TensorFlow 2, TensorFlow 1 will be faster. Then why did they take away this the graph altogether? Even TensorFlow 2 can do graph-based methodology. But in TensorFlow 2.0, every time you give a command, the command is immediately executed and you immediately get the results. It's not stored as part of the graph by default. The reason for that is, what they say is, if you're building a model and doing research on the model, what architecture, how many layers, how many blah, 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 then the graph-based method, it's a waste of time. Instead, I would like to know, okay, at this point, if I take this, make this change, what is the impact? TensorFlow 2.0 is known as eager execution. TensorFlow 1.0 is known as lazy execution. Eager execution is very handy when you want to do something and want to see the results quickly before the next step is executed. However, in TensorFlow 2.0, I can still create graphs by using what is called function decorators. Okay, but we'll not get into those things. If you're insisting on having a graph and you want to optimize the graph yourself, it's still possible. Extensive industry support. It's very popular amongst the deep neural network data scientists. Very easy to deploy, and the deployment can be done across servers. It can be deployed across mobile devices, web platforms. It's very versatile. And a lot of support for you on GitHub and Stack Overflow on TensorFlow. A lot of support. A lot of people give a lot of technical support there. All the big AI companies use it. And being a Google product, it continuously undergoes upgradations and changes based on the requirements. But at the same time, PyTorch also is a very powerful and very useful tool, PyTorch. So as I said in the morning, ideally you should be stepping into both. Let's start the journey here, but eventually down the line, see if you can get into PyTorch also. Both of them are equally good. Now TensorFlow is syntax wise not very difficult to learn, very easy to learn, but still it has a learning curve in it. It still has a learning curve. You cannot learn TensorFlow in a matter of a day or two. That's where Keras helps us out. Keras can be learned in a matter of just 1 day max. And when you use Keras and build your models, under the hood, it actually builds TensorFlow models for you. So Keras does it for you. Before I go into this, I wanted to give you the current architecture of TensorFlow. TensorFlow is based on C++, TensorFlow, TF, C++ libraries. TensorFlow, above this we have Python libraries also, and then we have, okay, let me put it this way, Keras, and there are various other APIs which sit over TensorFlow, right? So TensorFlow itself sits over C++. What is this other library names? I forgot. But we're going to use this. So when we build our models using Keras, it will actually build models in TensorFlow. TensorFlow will, all the functionalities are written in C++. C++, it's a very powerful and a very, fast compiler based language. That's why C++ is chosen over there. C++, Yeah, it supports Python. It supports Python, Java, and various other languages, but Python is the most popular one. Both PyTorch as the name suggests, Torch is the name of the execution engine developed by Facebook. Torch with wrappers for Python, that is PyTorch. TensorFlow with wrappers for Python is TensorFlow. Plus, you have Keras over and above that. If you read the history of this this particular thing, this combination, it's a very unique historical case. Both TensorFlow and Keras were developed and designed by Google engineers. But for some reason, they used to release these things as separate products into the open source, and Keras used to support various other utilities. In version 2.0, they have taken a decision. From now onwards, Keras will be available only under TensorFlow. Now, when you install TensorFlow 2.0, Keras would automatically also get installed. Earlier, we used to install these things separately. Those two groups in Google have come together and they have decided that Keras and TensorFlow will now get married. No more looking around, you support me, me support you kind of thing. Now, if you download TensorFlow, Keras comes automatically, and Keras will not support anything other than TensorFlow down the line. Supports all the major operating systems. We'll be using Windows, but Ubuntu is most prevalent Unix operating system, Ubuntu. But we are going to use we are going to use Windows 7 or later. These are the languages supported by TensorFlow. Python is by the choice, the default choice is Python, and C++, it's what it's built on. Go, Go. Surprisingly, it is a language by Google itself, but for some reason, either they have not pushed it, I don't know, but somehow it's not so popular, the language Go. If I talk to around 100 data scientists, if I ask them whether they use Go, probably 80 of them will say no. All 100 will say Python. Okay. Swift, again, Swift is a language, I don't know how popular it is in the market outside. Most popular is Python. All right, now let us, okay, by the way, one more thing, one important thing, TensorFlow can be run on CPUs. TensorFlow can be run on graphical processing unit GPUs. TensorFlows can also run on TPUs. TPUs are specific chips designed by Intel for Google. That is called tensor processing units. They are designed specifically for Google by Intel, TPUs. Okay, but to be able to run this TensorFlow with GPUs, while installing the TensorFlow, you have to mention that download TensorFlow for GPUs. And when you download TensorFlow for GPUs, you have to download one more tool, one more package or library that is called CUDA, C-U-D-A, CUDA. The name is very abstract name, CUDA. This CUDA library was designed by NVIDIA. You heard of this term, NVIDIA? What do they do? Yeah, they're popular in gaming. So they have come out with a library which is very fast and efficient in matrix operations and in parallelizing things, the matrix operations. And your neural network is all matrix operations. So if you want to use GPUs, you have to download NVIDIA's CUDA library. Once you do that, TensorFlow uses that to create a model, deep learning models, and run them on GPUs parallelly. If you don't download NVIDIA's CUDA library, then you cannot make use of this facility of running TensorFlow on GPUs. Even if you have GPUs, it will not use them. Okay. Some minor points, just keep in mind when you do your capstone, all these things might become handy. Right now, they will be of not much value in this session. Okay, all of you are able to see version 2.0 on your systems? Yeah. So let me take you through tensors first. See, when you work on these deep neural networks, okay, right now when we are working on these deep neural networks, this will not come out to be very important to you. That is that fact that you are working on tensors, and tensors can have different dimensions. But when you work in CNN, convolutional neural network, the input to CNN, convolutional neural network, which is an image, generally this image is shown as 3-dimensional volumes. If you're working videos, then it will be a 4-dimensional volumes. So this concept of volumes and how input volume is converted into output volumes, how do you measure the storage requirement of these volumes and all these things, this becomes very important when you're in CNN. Okay. However, still at this point, I'll just quickly show you what tensors are and how it's created. Come to this point, creating tensors. What are tensors? Tensors are basically objects which hold data. These objects could be a simple single value. That means tensors of 0 dimension, or they can be a list, tensor of 1 dimension, or they can be an array, tensor of 2 dimensions, so on and so forth. Some of the common ways in which you'll create tensors in your program is, say for example, you'll create a constant using tf.constant. I'm storing this string. The string is being stored in this variable. This variable hello here, this is called a tensor of the type constant. In neural network, we had a bias. In the bias, we have a constant value. So I can create a bias node by declaring it as a constant, tf.constant, and give the value as 1. I can create tensors using operations. I do operations on it, mathematical operations. For example, I've created a constant here called 3, basically storing the value of 3 in a variable, storing the value of 5 in another variable. I can use tf.add these two. The result which is created, this is again a tensor. Instead of constant, we can also have variables. Variables means those locations in memory whose value will change when the program is being executed. Your weights that you use in neural network, the weights have to be declared as variables. They cannot be declared as constants. So how do I declare? tf.variable, V capital, tf.variable, initial values, then you give the shape in which you want it to be. This is a shape of 2, 4. I'm going to create an array of 2, 4. So I'm giving a shape of 2, 4. You can give a name to the variable if you wish. What is the data type? What is the shape of this object which you're creating? Keep in mind, tensors can have multi-dimensions, so you have to give the shape. And then you give the values over here. When you do this, now look at this. Print a numpy will print this entire value over here, print the entire array. Print a shape. What is shape? Shape is 2, 4. But there is one more thing called rank. tf.rank a. Rank tells you how many dimensions are there. Shape tells you how long each dimension is. Please be careful about this differentiation, the difference between the two. Rank will tell you how many dimensions are there. How many dimensions are there for this array? Length into breadth, 2 dimensions. How long each dimension is, that is given by the shape. For example, the row dimension is 2 rows, that is 2. The column dimension is 4 columns. So this is my shape and this is my rank. Rank means how many dimensions. How many dimensions does this table have? 3 dimensions, so rank is 3. What is the length? What is the depth and what is the breadth? That is the shape. The width, all of them are same, then you got a cube. If length, breadth and width are not the same, then you got a parallelogram, something of that sort. So rank tells you how many dimensions are there in this object. Shape tells you what is the length of those dimensions. Look at this one. I'm creating here, observe carefully, this is a square bracket inside square brackets. So what I'm saying is arrange this as 1, 2, 3, 4 column wise. This is an array, okay. So when you look at the shape, there are 4 rows and all of them belong to 1 column. What is the rank of this? Rank of this is 2. Have you heard of lists? List. Only list object will have a rank of 1. A list has a rank of 1. Okay. Now, if I ask you what is the rank of this, looks like it's a rank of 1, but actually it's 2 ranks, because it'll create an array out of it. Array has rows and columns in it. This will be the way you defined it here. This will be arranged vertically 1, 2, 3, 4. Then it will be 1, 4. Then you will not have these brackets. These internal brackets show you that each one of them is one single row. Yeah, it's rows, columns. Some more examples here. Just get the concept in place, then we'll move on. Look at this. How will this be placed? This will be placed as 1, 2, below that 3, 4. Because there are brackets inside. This is first row, this is second row. So now the shape of this will be 2, 2. Rank will also be 2. This is another way of creating your tensor, tensor. This is basically a constant tensor which I'm creating. I'm saying replicate this 50 12 times. When you're replicating the 50 12 times, create 6 rows and 2 columns. So there are different ways of creating these tensors. Tensors can be constant, tensors can be variables. When you're building your deep neural network, all the weights have to be created as tensors which are variable types. The bias layer will be created as tensors which are constant type. You can also use convert to tensor. There's a command where I can take any Python object and convert into tensor. Convert to tensor does this. All the tensors have ranks and shapes. You should know what is the difference between a rank and a shape. Okay, any question till now? I'm just dealing with the very basic unit in which data is stored in TensorFlow. Those other dimensions we won't come across in normal data, but we'll definitely come across in image processing. Image processing, we have 4-dimensional data sets.
Okay. So
where if you use a color image is 3-dimensional volume. RGB with the pixels, how many pixels in rows and columns with RGB, it's a volume.
Okay. So always like based on this problem case, we are having like 2-dimensional.
Here we are having 2.
But it can support multiple dimensions.
Multiple also. Okay. Alright. Some more examples of TensorFlow. But what I want to show you is, go straight down. Let's do a simple linear regression here in TensorFlow. How do we do it? Okay. Now this is the linear equation which I want to represent in TensorFlow, where the output y is a product of wx plus b. Okay. So in this, I declare both this w, which is going to vary as variable, and b also I'm going to declare as that variable. This b is the b that comes into the equation of each neuron. I'm not talking the bias initialization node, the one. I'm not talking about that. So I'm declaring both of them as variable. I'm initializing them with certain values. The data type is float. Yeah. If you don't give the data type, default is int. Are you all okay? Simple declaration. Now here I'm saying, look at this, x is this variable. I'm declaring x as a variable because x will come from the data file. I'm declaring x as a variable, initializing with some value here right now. You print these things, you get the corresponding values and the data types and rank and shape, everything out. Now let's go ahead and build a linear model on this. Imagine this is my training data and this is the corresponding training output. So there is one variable x and there is one variable y. Y is dependent on x. I initialize my weights to 0. I initialize my bias also to 0. Why you're initializing to 0? No reason. You can initialize to anything that you want. It can be initialized to some random number also if you wish. I'm going to create training steps. Training steps means iterations, 100 iterations. Remember this learning rate? In the gradient descent, by how much you want to change the weights, by what fraction you want to change the learning rate. For I in range training steps, what it means is for I is equal to 1 to 100, yeah, for I is equal to 1 to 100, you can execute this code if you have this code with you. What I want you to do is, with TF gradient tape as tape, I will explain what this is to you in a moment. But I want to make sure that all of you with me till this point. Loops. Train step is how many loops you want to execute. You can call it anything you like. I can call it n loops, and I can say for I in range n loops. Okay. Well, what is this gradient tape? This is where I need to. It's kind of difficult to explain this because you have not used TF1, TensorFlow 1.0. In TensorFlow 1.0, what used to happen is, for every small, suppose you have two numbers A and B, and you're creating third number C is equal to A plus B. You have two numbers, A is equal to 5, and suppose B is equal to 10, and you're saying C is equal to add or A plus B. I told you it won't execute anything. At this point, it will know that you have to create a node in the graph called A. So a node will be created called A is equal to 5. You'll have to create a node called B is equal to 5. Then we'll come to this, it'll say, okay, these two have to be added, and then create a node C out of this. Until you say print C, nothing will happen, only this graph will be created. The moment you say print C, this graph will be converted into exe and executed. Same way, when you build any model, all the steps in the models will be converted into graph. Now, in linear regression, where I have to do a gradient descent, or forget linear regression, in neural network, where I have to do back propagation, in back propagation in the chain rule, I have to do dy by dx of the various steps. I have to start from the very end and go to the very first layer. I have to do a dy by dx of various steps, including nonlinear linear transformations. Remember that? That you will be able to do if you know the entire graph, how these steps are linked to each other. The dy by dx at every step will automatically be done for you by TensorFlow itself. But in TensorFlow 2.0, we don't have this graph concept. It is supported, but by default it is not. So what will happen is, every step will get executed independent of each other. There will be no such graph available. Now in that kind of situation where I want to do a chain equation, I don't know what the chain is, I don't know what the flow was. Every step is independent of other, there is no connection between them. So that automatic, the back propagation that used to happen, which we call gradient descent algorithm, that used to happen automatically in TensorFlow 1.0, will not happen in TensorFlow 2.0. So if you want to implement gradient descent in TensorFlow in 2.0, either you have to manually find out the link and express that in the gradient descent, or what we do is we use something called gradient tape. Gradient tape. Concept is very simple. This gradient tape is a function given to us in TensorFlow 2.0. What it does is, you know, tape recorders. When I used to go and attend lectures in my graduation days, we used to carry these recorders, keep it in the front, whatever the professor is saying, it gets recorded. Okay, so here also they provided a way of recording all these actions that you're taking into a tape. That is called gradient tape. They've given a name to it, gradient tape. So gradient tape is like a tape recorder, recording all the steps that you're executing in the loop. Once you have all these steps copied into a tape recorded version of this is available, then you can automatically apply the gradient descent using the tape recorder. That is the concept of gradient tape. So how do you do it? With gradient tape as tape, you can call it ABCD. So I have now switched on the tape recorder. Now I am doing my modeling. So I am saying that y is a function of this into w plus b. Whenever you get the y, find out the error between the predicted and actual. and my objective is to reduce the mean of this squared error. You see TF dot square error, this is going to create sum of squared errors. The sum of squared errors is sent through TF reduce mean. So if you observe this carefully, what we are doing here is reducing the mean sum of squared errors. We reduce mean sum of squared errors. No, who asked the question? In linear regression, the best fit line reduces the mean sum of squared errors. No, it's the same stuff. Are you all okay? Now all I need to do is find out the gradient, how much it has to change, find out how much the bias has to change. How do you find out? Just apply this tape. Use this tape recorded version. On this you apply the gradient descent algorithm using this loss function. So this will find out for me how much the weight and the bias should change. This will happen, the new weight will be the learning rate into the how much the weight has to change. Same way the new bias will be the learning rate into how much the bias has to change. Are you able to connect to this? Are these two okay? These two steps? Remember, new weight was old weight minus learning step into, that's what we are doing, the gradient of the W given the loss function, whatever the loss function was. This operation that you see here is what this is. That's it. You built a linear model here. What you have there is to print for every 20 steps you want to print out the metrics. Now when you run this, you will see that it's actually implementing gradient descent, and it's given the random starting points of W and your B. It is finding out the right kind of W and B, the optimal W and B, which gives the least error. You can run the code and see for yourself. I won't be able to run because of the TensorFlow problem, but you should be able to run the code and see the gradient descent in action. Are you able to see the gradient descent in action? You can even see the plot on the training and testing. So building a linear regression model is as easy as this. To make life for people like me who are very lazy even more easier. No. Actually, what we are doing is a toy example, but there are some real cases where this can become a dreaded thing. Actually, TensorFlow.
Question we discussed was we had the ultimate intention of neural network is to reduce the error to a minimal, and we are managing that by distributing the changing the weight and then refinding the errors. So the challenge here is the error at every layer, though we proportionately reduce it, again there is an input from the previous layer, which is weight, which also introduces new errors. So is there a possibility to have some control on where we can like instead of having this on all layers, can I do this only on few layers and leave the others at freedom?
Basically her question is, can we do gradient descent on only few layers rather than all the layers? Can we leave out some layers and not do the gradient descent? That's what she's asking. Yeah. So what's your answer to that? In the gradient descent backpropagation, all neurons get what we call allocated some errors, and all neurons in all layers, they adjust their weights. Our question is, can we restrict this to some layers, not all the layers? Come on again, Vinay. Can you pass on the mic to him, please, quickly?
If we, so if we do not use those particular neurons in the back propagation, maybe those neurons will not learn, right? So they will have that random weight, and that will not be that is, it is as if it is not existent at all, right? If it has not been learning.
Correct. That's correct. What I said is, if you do anything of that sort, then those neurons will not learn any weights. They'll stick with their old random weights. Okay, but technically that is possible that we do it. But this what we do is in CNN. In CNN, I'm building a model a deep neural network based model to do some image identification. But the amount of data set I have is not sufficient for me to do the training. My model will become easily overfit given the amount of data I have. I need large amount of data which I don't have. I can look for other open source model which have already been trained and have generalized well on similar data set. I can take all the architecture from there, borrow the weights from there, and I can freeze the first few layers. I'll say, boss, you people don't get updated, let rest of the layers get updated. I can do that in CNN. So in CNN, convolutional neural network, I can freeze some layers and make sure that they are not modified in the backprop. Other layers get modified in the backprop. Those things are possible technically, yes, but we don't use it in deep learning because what he said is correct, right? Those neurons will be left with random weights and they will not learn anything.
This tape that we are using, can you take us through one iteration of what the values will be at each level? And
can you take us to one iteration what values will be at each level? We can do that. That's not a problem. I won't be able to run it here because
no, that's okay.
But what you need to do is just keep printing these values out in every iteration.
So the tape works only until this loss, or does it go beyond that also? What does it actually record and reuse?
What does it record? Okay.
Analogy.
What this tape records is every step that you have taken here. You said that y hat is equal to this. So here there will be a graph created. The graph will have a node called train x. It will have a node called w. It will have a node called b. So train x and w will be multiplied first, multiplication operation. That will be added to the b addition operation. And that will give me y hat. So that is my graph. That sequence in which things have to be executed is what is noted down on the tape. Now when I want to do how the error changes when I change the w, I want to do dE by dW. For that dE by dW, I will do dE by dO by this linear equation, and linear equation by dW, right? So since that chain is maintained, I will be able to backpropagate my errors and go and modify the W and the B over here in the equation. I want to find out how the error changes dE by dW. This is equal to dE by how the output changes, dO. This is dO by d linear function, LF, the linear model. Okay, the linear model is y equal to mx plus c. And then into d of mx plus c by d of m. This is what I want to find out. Sorry, let's call it wx plus c. dw. This is w, this is w. This is what we have to find out, right? To find dE by dW, this is what I need to do, right? So derivation of wx plus c with respect to w is nothing but x. Okay. So how this error will change when I change w by a bit? I need to execute in this sequence. This sequence will be captured on the tape. In what sequence you're creating a graph that will be captured on the tape, and the back propagation will be applied using that tape, whatever is recorded on the tape. That concept is called gradient tape. This would not be possible in TensorFlow 2.0 because in TensorFlow 2.0 by default it doesn't maintain graphs. 1.0 maintains a graph for this. So there tf.gradient is automatic function available. We don't have that here. It's unfortunately not possible to do justice to TensorFlow in a matter of few hours. So I'm just showing you some key points, but there is a lot more to learn. And as I said earlier, those two blogs which I showed you have to go through those two blogs. They're for neural networks. For TensorFlow, I'll share with you some. You can go through online resources, but I'll share with you some 2 books using which you can quickly learn TensorFlow. Okay, but mostly we are going to work on Keras. All right, let's move on. TF 1.0, there was no eager execution, it was lazy execution, but TF 2.0, eager execution is the default. When we build our models using TensorFlow or Keras, we can build models in 2 ways. One is called sequential API, The other is called functional API. I'll try to show you both, but we'll start with sequential API, which is much more easier. Functional API is also easy. It's not difficult. That's also easy. But sequential API is easier. We'll see using sequential APIs. The beauty is, if you're expert in programming, especially C++, you can write your own classes. If people come from a software background will know class inheritance. People who don't come from software background, don't worry about these things. What it means is, we can tweak and tune the libraries available in TensorFlow to our needs. We can do that also using what is called subclassing. All this power is given to us by TensorFlow engineers. What I would like to show you is Keras. Earlier, Keras was available as a separate product, so you had to download TensorFlow 1.0, download Keras separately. But today, both of them have integrated, made for each other. So when you download TensorFlow 2.0, Keras automatically comes bundled, and you are advised to use TensorFlow Keras, not the standalone Keras. Because the kind of functionalities they have built in, the kind of support they give in TensorFlow Keras, you won't find it in standalone Keras. Standalone Keras will eventually be stopped. They will stop supporting it. Okay. When? We have no idea. So instead of Keras, we will use tf.keras. I'll show you all these things in the code. We'll see all these things in the code. Let's go to the code and see all these things. This is the same wines dataset which is available on UCI. One is called white wine, one is called red wine. White wine and red wine, okay? What I'm going to do is, I'm going to combine these two into one single file, because both of them have same structure, same column types. I'm going to combine the white wine and the red wines together into one single file and see if we can build a neural network based model which is able to classify these two wines properly. So the deep neural network based model should be able to understand the relationship between these independent variables and the class. The class being red or white, the target variable. So let's see if the deep neural network can do a good job here. Can it understand the pattern, the relationship between x and y? X being your independent variables, y being the class of the wine. Okay. Please run the code. The code is runnable. In my case, TensorFlow is going to give a problem, but let me run this. Let's see. Shift enter. Shift enter. We don't need to do df describe and all these things. If you want to do it, do it. Null, PD null is also not required. We know there's no problem here. The number of records also 4898. You want to run it, please run it. I have no problems. This matplotlib inline, just execute this line, otherwise the plot is also not required. Okay. Okay, let's not be lazy, let's run it. I'm not going to do a df describe. These are all kind of not required now. I'm going to run this matplotlib, shift enter. I'm not going to generate pair plot. We have seen this many times. Yeah. So I'm going to leave it to you. You want to run it, run it. Otherwise, let's move on. Pair plot for red wines, pair plot for white wines. Come straight down to this line. What I'm doing here is, I'm introducing a column, new column. The column name is type. For the red wines, I'm putting a 1. For the white wines, I'm keeping a 0. So this is a binary classification problem. By looking at the input X, can I decide what type of wine is it? Is it red wine or white wine? That is a question. From your train test, you split this data, shift enter, shift enter. You can have a look at your test data. Some of the wines are red, some of the wines are white. Only in this case, only 3 of them are red, rest of them are white. Convert them into standard scalar, z-scores. Till now, we have not done anything new. We have done what is traditional. Now we are stepping into deep neural networks. Now, given the data I have with me, now let's see how deep neural network performs. Now be careful here. when you go back and build models, don't say from Keras. That is also possible, but that is version 1.0. What we are using is from TensorFlow.Keras, the Keras that comes bundled with TensorFlow. From there, you import sequential. Sequential is a function available to us to create our deep learning models. Okay, I'm going to use sequential method for creating models. So from the layers, the first I import is a dense layer. Does the word dense sound a bell? Dense neural networks, dense layers. So what you're going to do here is create dense neural network. That's what this dense is going to do. Are you all with me? Okay. Next line, I'm creating an empty model. This is what we call initializing the models. We are creating an empty model using this command sequential. What is a sequential? Sequential is a way of creating the models. So I'm creating an empty model here. To this empty model, I'm going to add a dense layer. The dense layer has 12 neurons. Why 12? You can have 1200 if you wish. You can have 1 if you wish. You can have 10 if you wish. It's your choice. How many neurons per layer is a hyperparameter. But usually what I do is, what I suggest is, how many columns do you have in this? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 and 12. At least have as many neurons, as many columns. The more the neurons you have, the higher the dimensions you are projecting your data into. If the input data is 12 dimensional and the number of neurons you have in the first layer is 3, then you are reducing your dimensions from 12 to 3. Whereas what Cover's theorem says is you should project your data into higher dimensions. That's why I'm keeping 12 here. If you want, you can go beyond 12 also. Are you able to run this? So I'm creating 12 neurons. In every neuron of that first layer, the activation should be sigmoid. You know what is a sigmoid function, right? And the input shape, the record which comes in, what is the shape of the input? The shape of the input is 11 comma. The number of columns you have there minus quality, 12 minus quality is 11. So you have 11 input columns. So input shape is 11 comma. Comma means open bracket. Open means any number can come in there. So I'm going to have, every record is going to have 11 columns in the input. So what this is going to do is, your first input layer will be 11. 1, 2, 3, 4, dot, 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 11. This is 1, this is 11. And you have 12 neurons. 12. This is 1. So all the 11 is going to go to every neuron. All the 11 is going to go to every neuron. So how many weights will be there here? 11 into 12 plus 12. This many weights will be created between the first input layer and the first hidden layer. How did this 12 come? There will be bias node here. The bias node will be connected to all the neurons. So these are the 12 weights which you have to learn. So the number of weights to be learnt between the first input layer and the first hidden layer is this many in this case. I'm not happy with the first hidden layer. You can add one more. Model.add dense. Now how many layers are, how many neurons are adding here? You are adding 8 neurons here. So this is 1, this is 8. How many weights will be learnt between the first hidden layer and second hidden layer? Yes, 12 into 8 plus 8. This many weights will be learnt over here in this region. And then finally last one, it's a binary classification. Since it's a binary classification in the output layer, I just need 1 neuron. So I add model.add dense activation sigmoid. So what we have essentially done here is, we created a model, a deep neural network based model, where we have 12 neurons. We have 12 neurons in the first layer, first hidden layer, H1, starting from 1 to 12. and in H2 we have 8, 1 to 8, and then in the output layer we have 1 neuron, and in the input layer we have how many? Input layer IL 11. This is 11. So this is the neural network architecture you have created till now. This is what you have done. But these are only neurons which have been arranged. Now comes the question, how do you define error here? And what optimization algorithm do you want to use to minimize the error across? That comes in the compile statement. Look at the model.compile. In model.compile, the loss function, the error function which I want to use is binary cross entropy, log loss function. And optimizer which I want to use, instead of using SGD, the vanilla gradient descent, I'm using another one called ADAM. Okay. So when you're doing this back propagation and reducing the loss function, which metrics do you want to keep your eye on? I want to keep an eye on my overall accuracy of the model. Once you've done this, once you compile the model, now the model is ready as executable. So merely defining these layers will not be useful. These are just a bunch of neurons. But how do you find out the error done by these neurons, and how do you optimize that error across the neurons? That is done by the model.compile. Now once you've done the compilation, your model is ready for execution. So let's first train it. For training we do model.fit, just like we did earlier. We do model.fit, xtrain, ytrain, right? So I'm going to use fit function. Fit function, I'm giving xtrain, ytrain, and I'm giving something called epochs. You won't have heard about epochs earlier, have you? Epochs. Okay, I'll tell you what epochs is, and I'll tell you what batch size also is. Go ahead and run this. When you run this, you will see this log file. Learning rates is default. I think 0.01 is the default there. All hyperparameters are default values if you don't specify. Are you able to see the epochs unfolding? I'll tell you what these epochs are, but keep an eye on their accuracy scores. Done? 20 operations. We don't need to do predict and all, but if you want to do predict, do it. But what I would like you to do is print out the accuracy scores which I have given as for both training and testing. Always test your model both against training data and test data. If accuracy in training is very high, performance in test is very poor, you're in overfit zone. If accuracy in both training and testing is poor, you're in underfit zone. If accuracy in both training and testing is almost similar and more as per expected, then you can claim that you're in right fit. Okay, and as we can see, both in testing and training, it's giving me 99% accuracy. But neural network, being famous for getting stuck in local minimas, when you next time run this, unless you use random state somewhere, you'll get different result here. But since the neural network here in this case is very small neural network, it's not very large neural network, the local minimas will be very less, and you'll often find yourself around the same kind of accuracy scores, different accuracies but similar range. You can run it again and see it for yourselves. And on this, when I do my confusion matrix, look at the confusion matrix, the red wine and the white wine. This is my true positives, 495. This is my true negatives. Very high score. Only 9 records out of the total records misclassified. That is why this is the loss function, how the loss function has decreased over the epochs. The loss function fell down sharply around the first 10 epochs itself. We don't even need to go to 20 epochs. In the first 10 epochs itself, we get a very good score. Now, what is epochs? Let me tell you that. We use deep neural network when the data sets are very complex. We won't use deep neural network for predicting miles per gallon given the various characteristics. Those are all simple data sets. So we use deep neural networks when we think the relationship between x and y is going to be a very complex relationship. Not a simple linear relationship kind of thing. Okay? In such cases, if this is my training set, this is the X and the Y, then reading this data once by your neural network model to do the prediction, the one reading of this data may not be sufficient for us to understand all the relationship between X and Y. Not difficult. We have seen this in our own case when we were preparing for board exams. One single reading of that chemistry book was not enough. We had to go through that chemistry book multiple times to understand the equations. So sometimes when things are complex, one pass of the data will not be sufficient to understand all the complexity in the data, complexity in the relationship between X and Y. So you'll have to read that data again and again to understand all the complexities hidden in the data set. As many times as you read this training file, that is called epoch, E-P-O-C-H. How many times you want to read the data file before you say that your model is trained? We have given 100. 100, right? 20, sorry, we have given 20 epochs. That means the data file will read 20 times to train your model. Same data set again and again it will be read.
The weights
Yes.
from the output node to the input node.
Correct.
Not the epoch.
No, not this epoch. So, in a very algorithmic way, what we write is for epoch is equal to 1 to 20, as in our case. Read the data file completely once, then while error gradient not 0, do a forward prop, backward prop. Do a forward prop, backward prop, end while. Now you understand epoch and backward forward? The backward forward propagation that happens, okay, I'm assuming that we're going to read the entire data set once for the forward propagation, backward propagation. So I want to read the data file 20 times. Each time I read, I want to do the forward propagation, backward propagation. So forward propagation, backward propagation is subsumed by the epochs. Each epoch is the full file. Just read the entire file once. Do forward, backward. Ask Karthik, why are you scared? What is holding you back? Telling us. Don't worry. Pick up the mic, it's next to you. No, epoch is not backward. Hey guys, simple. At least that's why I relate to epochs. When you prepared for your exams, mathematics was trigonometry was so tough. One reading of the chapter was not enough for me to be able to crack all the problems at the end. So I had to go back. Okay, I'm not able to solve this problem. Let me go back and read the chapter again. That is second epoch. And come back and see if I can solve the problems again. Again, I'm stuck with some problem. I'm not sufficient. Go back and read. So that is my third epoch. So epochs is how many times you need to read your data file to be able to extract the patterns between X and Y.
With each epoch, the weights assigned will be different.
What do you mean by that?
Like for example, let's take one x1. In the first epoch, the weight will be w1. It's random anyway, right? So in the second epoch, the weight will be different.
The stepping, a very important question. Did you hear the question? You have any questions, guys? Same question. Okay. Can you repeat the question again?
With every epoch, the weight assigned for a particular
will the weights be randomized again?
Randomized again.
No.
Will it be different?
No. With each reading of the chapter of the book, do I forget what I learned earlier?
But
Yes or no? No, right? Similarly, in this case, here also, with each subsequent epoch, it will fine-tune the weights learnt by the previous epoch.
But it will be different. It won't be random, but it will be different.
It will keep on moving, it will keep on different. It will be different. So first epoch, through backward whatever it came down and settled at some weights. Now you'll start a second epoch. In second epoch, again the forward propagation will happen. All the data will, some error will come. Again the weights have to be, it will try to reduce the weight, further fine tune the weights. It's not forgetting the weights.
In that case, what is the significance of reading the file again? Can we not increase the number of backward and forward propagations? It's going to be.
We have no control over forward backward propagations. These in fact, okay, this forward good question again. Can you ask this question again? Shoot it.
If the weights.
Today you had Horlicks in breakfast.
I really don't know if it's okay. Fine. So if we are going to have the epoch, the weights from the previous forward backward propagation, then we can increase the number of times we do the forward backward propagation instead of having epochs. What is different?
Okay, what is the answer again?
What I said was she was asking why don't we change the number of times
Correct.
forward and backward gets executed.
Yeah.
But we don't have control over it because it depends on the gradient, and once the gradient reaches, as you have written, while error gradient goes to 0, then you stop. So we don't have to control it. It just depends on the gradient. And my question would be for if the gradient is going to go to 0, then you have already reached the optimal output. Why do you have to redo it?
Hopefully you're not stuck in the local minima. If you're stuck in local minima, all the epochs are useless. I told you this morning, the error function is such that you're stuck on some flat regions, or flat regions or local minimas. All subsequent epochs are useless, waste of time, computational resource wastage. Okay. But what happens is, all these forward backward propagations, all these loops, like in k-means clustering, for example, you remember k-means clustering? We have done unsupervised learning method k-means clustering. You start with initial centroids, but the centroids keep on shifting based on every iteration of the k-means clustering. Agreed? All these loops which are built into these systems, they are not infinite loops. After some loops, when the converging is not happening, the loop will break. Just like in k-means clustering, when the centroids are not converging, that keeps moving infinitely, the loop is broken. Same way here also, the forward backward propagation, when the error is not converging to 0, it's not converging. After certain iteration, even it will stop. Even that inner loop will stop. It will not. I have given as gradient is equal to 0, but that is an ideal case. It will stop. Then I have to consider those weights as starting weights and redo the iteration again. That is what second epoch will help me. However, if in the first epoch itself, you are stuck in some flat regions of your error function or some local minimas of error function, as you will see yourselves when you do this hands-on, subsequent iterations will be useless. Okay, subsequent epochs will be a waste of computational resource. What I would like you to do is, look at this log file which you have generated. In this log file, look at the loss. And if you look at the loss, somewhere around, okay, in my case it's, okay. The drop in loss is, look at this, from 0.16 it dropped to 0.03. From 0.03 it came to 0.2. This is across epochs, the third epoch. In the third epoch, after reading all the files and doing things, my loss came down to 0.2. But after this, it's 0.2, 0.2, 0.2, 0.2, 0.2. And then 0.197, very insignificant drops. If you look at the loss function here, the first loss was very first drop of loss was very significant. Up till the fifth epoch, it was, we can say that loss was significant. But after the fifth, you see the gradient of this loss function is almost flat. All these epochs that you're executing here, from 20th to say 10 onwards, 10 to 20th, all these epochs that you have executed, these epochs have given you a very fractional drop in the loss, very tiny fraction. So these epochs are either useless, or your model is absorbing the noise in the data and reducing the loss. This loss is because of the random weights. From the random weights, some ideal weights were found. So this loss was because of that. But all subsequent loss especially after the 10th epoch, all the subsequent loss which you're seeing is fractional loss, and you increase this from 20 epochs to 200 epochs, you will see that this goes towards 0. But it may not become 0, it will come inch towards 0, 0, 0, 0, but not 0. you are absorbing the noise in the data and representing that as a pattern in your training set, because of it the loss is going down insignificantly. So what I'm saying here is, if you have too many epochs, you might be overfit. You have to find out the right value of number of epochs, after which we think that the model's loss is going down in training set because of the model absorbing noise, not real information. So coming back to your question, what if the algorithm has already reached a point where the gradient is 0? All subsequent epochs are useless. As in this case, we are wasting our computational resource. But we might be in a, when you're dealing with images and voice and all these things, we might be in a situation where the first few epochs are not sufficient to reduce this loss. If I have some more epochs, I'll reduce the loss further without absorbing noise. That is called early stopping. We have an option called early stopping available in Keras, where if you use that option, what Keras will do is, it'll keep an eye on the loss. If the loss is not reducing significantly, it'll cut the epochs. It will not do the subsequent epochs. That is called early stopping. Yeah, yes. Can you tell me why? Yes. Can you tell me why? Yes, you're right. Good observation. Look at the accuracy column. Isn't it going like a seismograph? That's what I told you. The final neural network level error function will go down like a seismograph. Suddenly it will go up, then it will go down. That's what you're observing. You need to take a stand on where you need to stop based on your comparison between training accuracy and test accuracy. If the two start deviating, that means either you're overfitting or underfitting. There's no other way. You have to compare both in training and testing to see whether you're in the right fit. All hyperparameters grid search. So which loss function to use, which activation function to use, how many layers do you have, how many neurons per layer, how many epochs, all these are hyperparameters. That's why I'm saying that we first need to get our concepts in place. Doing all these things is not difficult. We'll build one more neural network now, but before we go that, let's understand what's the question, what is the discussion.
Let's imagine our iteration. Now, in the first epoch, we have done quite a lot of forward and backward navigations. And I believe the last one will be a last forward navigation. And we have found the error. With that, one epoch is complete. So, now again, when the next epoch starts, it will use the previous weights and start all over. So, the last backward is not done in the previous epoch.
Last backward is not done in the previous. Last backward iteration in the previous epoch, that has adjusted the weights.
Okay, it will adjust the weights.
Now the next epoch when it starts, these will be the starting weights for it.
So, so it's kind of like we don't trust that the machine has found the best error and we are asking it to do it again. Or what is the difference between continuing the same epoch or doing it in...
No, these loops that are built for backward-forward propagation, just like in k-means clustering, if they're not improving beyond a point, they will actually break.
They will. So that's what. So we don't, we believe it may not be the best and we are asking it to repeat.
Correct.
Again from the previous one.
Correct.
So it's much like if we don't have the concept of epoch, if we assume like there are 20 backward and forward navigation in one epoch, instead of doing 20, I'm asking it to do like 200 epochs.
Yes.
It's all the same.
Yes, correct. Now in the dataset which I have used here, Wine's dataset, it's not ideal for deep learning. But when you use an image dataset, as I think I'll show you an example. Image dataset, images are very complex functions. The relationship between the class of the object and the characteristics of the object in terms of pixel values, that function is very complex function, and that function cannot be learned. That relationship cannot be learned many times using just one single epoch. To understand the relationship properly between the target class and the variables, it needs multiple epochs. There you will actually see across a lot of epochs the error comes down gradually. Here what you are seeing is come down plump and then it goes like this. That is only in this data set. But in those complex data set, you will see it's smooth like the elbow plot in k-means clustering. You see that there you will understand the epochs, importance of epochs. Yeah, but your question, whatever you said is also right. It's equivalent of increasing the number of backward forward propagation by using epochs. Hey, hold, use a mic. He's asking a question, let him ask, then I'll come to you.
If epochs, you're going to forward and backward propagate multiple times to reach a certain error value, which is the lowest for that particular epoch.
No, that's what I'm saying. Okay, go ahead, shoot.
Yeah, so when it's reaching the lowest point, so it says that I'm coming out of the loop, that while loop, it'll exit
No,
the
this
loop.
is not what I've written here is in haste. This should be while error gradient and not improving, not say 0. I should be saying that.
Okay, it's not improving means it's the lowest
It's significant.
error, the lowest error that it can
In that epoch.
Yeah, for that epoch. So it comes out of the loop and goes to the next epoch.
Correct.
And it has the same data set.
Starting with these initial weights.
Yeah, initial weights and the same data set.
Correct.
It would have reached the minimum lowest point because the previous epoch would have reached the lowest point because it has a flat region or the
Well, if you're in that flat region or in the local minima, all subsequent epochs are useless.
okay.
But if you're residing on a very low gradient plane, as I told you, some planes will have very small gradient. They'll take long time to cross the gradient. If you're stuck there,
So, but even if you go to the next epoch, the same time is going to be taken by that also. The second
it will
epoch,
take.
Yeah.
It will take.
Then why do you have to go to the second epoch?
The reason why we need to do that is, look at this. See, for this you need to understand the error functions. We are not in this error function at all. This is only in simple linear regression model. When you're dealing with deep neural networks, your error functions could be very small flat region. It's not 0 exactly. Okay. And then you might have your global minima here. To make it more realistic, I'll also give you local minima here. Yeah. Now let's assume that you are stuck here in the first epoch itself. All subsequent epochs are useless. Instead of being stuck here, suppose you're stuck in this point over here where the gradient is very small, not 0. Very small fraction, not 0. It's very sluggish and it's not moving forwards. There, that first set of forward-backward iterations may not be sufficient. They might come out of that when they reach the number of limits of iterations. So in the second epoch, when I start, I'll continue to push this. But second epoch itself may not be sufficient. Maybe at the 10th epoch, I would have reached this cusp where it significantly drops. So what you'll see is, in the first few epochs, the drop was significant. After that, it became flat. And somewhere around 10th epoch, it found the global minimum.
Why wouldn't it continue the same position, the cusp you're talking about, before the cusp when it's the lower gradient?
Yeah.
Why wouldn't it continue? Because we haven't fixed any
No, we don't.
limits. We don't fix it.
The loops have internal limits. They can't count.
How do you
When it goes to infinity, K-means clustering, it breaks the loop. Same way, all these internal loops, when they run for a certain amount of time and they don't reach the solution, they break the loop.
So the second loop will start from there. The epoch function will start from that point onwards.
The weights which has left behind
new
the
weights
place.
and it will go through the same order of
Yes.
the input data.
Yes. The data remains the same input data, no change. But if you get stuck in local minimas and all, it's no use. If you're stuck anywhere here, all subsequent epochs will be useless. So you have to keep an eye on this log file, and to keep an eye on this log file, we use something called early stopping. What early stopping does is, it keeps an eye on this loss. If the loss is not improving between two iterations, or if the loss starts going up, then the early stopping mechanism will cut your epochs. So your epochs will end here itself in the first 10 or before 10 itself it will stop. Shall we see one more example? We'll see an example with a more complex data set. Wine's data set is actually not for deep neural network, it's more for decision tree and other things. Let's see one more example. This example is MNIST data set. I had noted down somewhere what this MNIST is, what this CUDA is. I don't know where I kept it. Let me just check if I have it. And This MNIST data set is basically handwritten digits data set. The data was collected I think from the post office, where people write the numbers in particular way. So they've taken a picture of those handwritten digits and they converted those pictures into 28 by 28 grayscale images. So this 28 by 28 grayscale images, this is for example how 0 is written. Now what will happen is 28 by 28 means 28 pixels on this side and 28 pixels on horizontal side. 28 into 28 is 784 I think. 28 into 28 is equal to 784. So what will happen is your 28 by 28 image, which will actually be flattened out, and this flattened array will have 784 elements. 784. This will be your input record. Okay. Now in this input record, please look at this carefully. If you have somebody written a 0, some pixels will be bright, some pixels will be dark. There will always be a pattern of how 0 pixel distribution is, how the pixel intensity distribution is for 0. Whether you write 0 or I write 0, when you convert into 28 by 28, always some pixels will be bright, some pixels will be dark, some pixels will be intermediate, the grayscale. Okay, so the pattern will be hidden in this 784 elements, which tells you that this is a 0. Where the 784 elements are nothing but values ranging from 0 to 255. 0 means black, 255 means white. Similarly, if you have somebody written here 1, all of us write 1 on a piece of paper, I convert that into 28 into 28, then you will notice that some pixels here will have certain values, others will be zeros. So there will be a pattern hidden here, pattern which represents the relationship between the pixel intensities in this versus the label over here. So this is my y, this is my x. X consists of x1 to x784, 784 attributes. Now objective is, can we using deep neural network find out what this relationship is between this and this and express it in form of the weights. Are you all with me? You understand what's going on here? Yeah, so let's do it. How do you do that? I'm going to import from TensorFlow Keras. We have some data sets available. Of the data set, the one which I'm going to use is called MNIST.
So in this tutorial, we have learned about deep learning and how can you implement those deep learning technique using the API called Keras. I hope this will help you to understand how can you start working with Keras. And if you want to get updated with the new content like this, then please do subscribe Great Learning and also put a comment to the comment section that how you feel about the tutorial. And if you want to do courses on this topics, then please go to Great Learning Academy, where you will get almost 80 plus free courses, and after complete your course you can claim your certificate as well. And if you want to do these courses in your mobile application, that is also possible using Great Learning app. Thank you so much.